In this module, we will discuss supervised learning methods that can be applied to high-dimensional data, which are when the number of covariates exceeds the number of samples, such as those arising from high-throughput genomic assays. As a reminder, we have already discussed the preprocessing methods including image analysis for array-based data and alignment for RNA-seq-based data, normalization, and expression summaries. Once we have the expression summaries, we then performed our planned statistical analysis. We will now focus on the task of supervised learning, or in other words, predictive modeling. There are two large taxonomies describing analyses of high-throughput genomic data, which are referred to as supervised learning and unsupervised learning. Supervised learning incorporates knowledge of phenotypic information of the samples being examined. In Modules 7 and 8, we discussed the general problem of when there are two known classes or phenotypes, such as healthy versus diseased tissue samples, and differential expression analysis is performed to determine whether there are significant differences in gene expression comparing the two classes. We also covered differential expression analysis when there are more than two classes under study, such as comparing expression among the 4 tumor node metastasis stages for a solid tumor. We could also identify what genes are significantly related to a quantitative phenotype, or in other words, a continuous trait, such as systolic blood pressure, by fitting gene-level linear models. Thus, differential expression is also referred to as feature selection. Supervised learning also encompasses prediction, that is, fitting a multivariable model that is predictive of group membership or predictive of a quantitative phenotype. In the last module, we discussed unsupervised learning, which refers to an analysis where phenotypic data are either not available or are not used in the analysis, and the goal is to use only the expression values to discover structure in the data, such as clusters. This week, we will focus on predictive modeling. When selecting a statistical or predictive model, we need to think about the study design, the scale of measurement of the data, and what assumptions correspond to the statistical model. In this course, we have presumed that the data from a high-throughput genomic study need to be analyzed and have not focused on the study design. However, the study design may impact, to some extent, how we fit a predictive model. For example, when the study design is an experiment, the investigator fixes one or more factors. Given one or more factors are under the control of the investigator and all other variables are due to random assignment, only those factors that are under control of the investigator are independent variables in our predictive model. Clinical trials are a type of experiment whereby subjects are randomly assigned to a treatment, and the goal of the clinical trial is to observe the effect of the assigned treatment on some health outcome. Observational studies are when the data are collected from a naturally occurring situation. Observational studies are used when experiments are either unethical, unreasonable, and/or impractical to conduct. For example, suppose a researcher would like to conduct a study of the effects of smoking on cardiovascular disease. A possible experimental design would be to randomize 1,000 people to one of two groups, to smoke or to not smoke. After 10 years, the researcher plans to measure the incidence of cardiovascular disease and compare the two groups. This experiment would never be carried out because it is unethical to assign people to smoke or not smoke. Following subjects for 10 years is too long. Some smokers would not quit smoking in order to participate, so there would be non-compliance issues among the experimental subjects. And supplying 500 people with 10 years' worth of cigarettes would be cost prohibitive. Instead, we could perform an observational studies where we select 500 patients or cases with cardiovascular disease and 500 patients or controls without cardiovascular disease, and then develop a statistical model to identify what variables are significant predictors of case versus control. The disadvantages of observational studies include that subjects are not randomized to groups, and therefore, any observed differences cannot be directly attributed to the difference between groups, which are the smoking and not smoking groups. Also, other factors that are not held constant may attribute to the observed differences. For example, Smokers often drink alcohol, and maybe smokers are older. Therefore, when the study is observational, you may need to control for other confounding factors. In this module, we will focus on methods for predicting a continuous response and a binary response. Statistical methods are appropriate for designated scales of measurement. When predicting a continuous response, we often use linear regression. In this and the next module, we will discuss other methods for predicting a continuous response that can accommodate high-dimensional data, including penalized linear regression, regression trees, and random forests. When predicting a binary or dichotomous class response, we often use logistic regression. In this and the next module, we will discuss other methods for predicting a binary response that can accommodate high-dimensional data, including penalized logistic regression, classification trees, random forests, and k-nearest neighbors. When predicting a multi-level nominal response, that is, you have more than two groups, we typically use multinomial regression. When predicting an ordinal response, most will use a cumulative logit model. When predicting a time-to-event response, such as overall survival, most use Cox proportional hazards model or accelerated failure time models. For these and other scales of response variables, there are high-dimensional solutions as well, though they will not be discussed in this course. First, we will discuss predicting a quantitative phenotype, or in other words, a continuous variable. When building a predictive model using gene expression data as covariates, we may want to fit a multivariable linear regression model. Let's return to the simple linear regression model first. This should look familiar as we reviewed the simple linear regression model in the normalization module. Given we have a set of data, how can we fit the regression line? Our goal is to find the line that minimizes the vertical distances to the data points. In fitting a line to the data, we postulate that there is a probability distribution of y for each level of x. And the means of the probability distribution vary in some systematic fashion with x. So regression considers the frequency distribution of one variable when another is held fixed at each of several levels. Our goal is to fit a line that permits some error, since the linear relationship is not perfect. And the model we will use is given by this equation, where y sub I is the response or dependent variable, beta naught is the intercept, beta 1 is the slope coefficient, x sub I is the independent or predictor variable, and e sub I is the error, and the expected value of the error is equal to 0, and the variance of the error terms is sigma squared. Thus, the expected value of y sub I is given by this equation. Note that in simple linear regression, there are three parameters, beta naught, beta 1, and sigma squared. Because we do not know the values of the slope and intercept for the best line, we need to estimate them using data. The method of least squares considers the deviation of y sub I from its expected value, beta naught plus beta 1 times x sub I. To fit a line to these data such that the vertical distances from the fitted value to the data points is minimized, we want to minimize this equation. To find the intercept and slope that minimize our objective function q, we take the derivative of q with respect to beta naught and also take the derivative of q with respect to beta 1, and we get these two equations. Setting both equations equal to 0, we have two equations and two unknowns, which can be solved simultaneously. After solving, we get this equation for the slope and this equation for the intercept. Of course, we won't be using these formulas in this course, but rather we will use R to fit a linear regression model for us. The function for fitting a linear model is Lm, and the response is modeled by the predictor variable, which, if these are stored in a data frame, the name of the data frame is passed to the data argument. Most often, we want to use the fitted models to perform various other tasks, so we put the linear model fit in an object using the assignment statement. For example, We could then use the summary function on our fitted model object to get information about the fitted regression model. The fitted values from the sample data are obtained by substituting the x values in the sample into the estimated regression function. The R function predict returns the fitted value. We may not have one predictor variable, but instead a set of p predictor variables. To study the relationship between a continuous outcome and several explanatory variables, we will use multiple linear regression. We often use multiple linear regression to control for confounders or improve the precision of our model predicting a continuous outcome y. When fitting a multiple linear regression model, we may be interested in estimation, that is, estimating how much y changes when x sub j changes, taking into account the effects of all other variables. Or we may be interested in understanding the effect of multiple predictors, that is, testing whether the x's collectively explain y. Another interest may be prediction. This is when you derive a multiple linear regression model, and then when observing a new set of subjects, you use their covariate values to predict their response y. Here is how we write the multiple linear regression model. The expected value of y given the predictors x is given by this equation. Beta naught is the expected value or mean value when all predictors equal 0, which may or may not be meaningful. Beta j is the change in the expected value of y for a 1-unit change in x, holding all other predictors constant. So in simple linear regression, there are 3 parameters, beta naught, beta 1, and sigma squared. Whereas for multiple linear regression, there are parameters for beta naught, p parameters for beta 1 through beta p, and sigma squared. We still use ordinary least squares to minimize the sum of squared errors to obtain the least squares estimates. But now there are p plus 1 betas, so it is not easy to write down the estimation formulas for each beta, so we only use software for obtaining the solution. The predictor variables may be continuous, binary, or multi-level categorical variables. For illustration, suppose we have a data set that includes men with prostate cancer, and we are interested in predicting log of prostate-specific antigen, using multiple predictor variables, including a continuous variable, a binary variable, where 1 indicates seminal vesicle invasion and 0 indicates no seminal vesicle invasion, and a multi-level categorical variable, Gleason grade, which takes on levels 6, 7, or 8 and greater. We can still use the LM function where our continuous response, LPSA, is modeled by these predictor variables on the right-hand side of the equation, where the data frame is prostate. In R, any variable stored as a factor will always be entered into the model using dummy variables. For Gleason grade, it is a multi-level factor, therefore it is included in the model using dummy variables. That is, because Gleason grade is either 6, 7, or greater than or equal to 8, R entered 2 dummy variables, Gleason 7, which is 1 if Gleason grade is 7 and 0 otherwise, and Gleason 8, which is 1 if Gleason grade is 8 or higher and 0 otherwise. If Gleason 7 equals 0 and Gleason 8 equals 0, that represents a subject whose Gleason grade 6. That is why for a k-level multi-level factor, you only need k-1 dummy variables. We can see the fitted model using the summary function. Beta naught is interpreted as the estimated value of y when all other covariates in the model equal 0. For our model, this would be when the log cancer volume is 0, there is no seminal vesicle invasion, and when Gleason grade is 6, because that is the subject when all covariates in the model are 0. As with simple linear regression, beta naught may not be scientifically relevant to interpret. In our case, all subjects are men with prostate cancer, so no subject has a log cancer volume of 0. Beta j is the estimate of the partial slope of x sub j, or the effect of x sub j controlling for all other x's in the model. It can be interpreted as the estimated mean change of y for a 1-unit increase in x sub j, holding all other covariates constant. This can also be said to be the effect of x sub j controlling for or adjusting for the effect of other covariates. You should be specific when interpreting these estimates. That is, don't simply say holding all other covariates constant, but actually list the variables. When interpreting the model parameters, we could make statements such as, for a 1-unit increase in log cancer volume, the log prostate-specific antigen is estimated to increase by 0.5612, controlling for seminal vesicle invasion and Gleason grade. We could also say, for a 1-unit increase in seminal vesicle invasion, log prostate-specific antigen is estimated to increase by 0.445. Note though, because seminal vesicle invasion, or SVI, is a binary variable, a 1-unit increase in SVI is moving from no seminal vesicle invasion to having seminal vesicle invasion. So in the context of this data set, it is more informative to state that those with seminal vesicle invasion are estimated to have a log prostate-specific antigen 0.445 units higher than those without seminal vesicle invasion, controlling for log cancer volume and Gleason grade. For Gleason grade, those with Gleason grade of 7 are estimated to have a log prostate-specific antigen 0.3668 units higher than those with a Gleason grade of 6, controlling for log cancer volume and SVI, and those with a Gleason grade of 8 are estimated to have a log prostate-specific antigen 0.1152 units lower than those with a Gleason grade of 6, controlling for log cancer volume and seminal vesicle invasion. To illustrate why this is the correct interpretation for beta sub j, suppose this is our multiple linear regression model. Now consider two subjects. In this example, one has SVI equal 1 and the other has SVI equal 0, but all other covariates are fixed. That is, for both subjects, log cancer value takes some value c, and for both subjects, the dummy codes for the two levels of Gleason grade are the same. The expected value for the subject with SVI equals 1 is given by this equation, whereas the expected value for the subject with SVI equals 0 is given by this equation. Subtracting the second equation from the first yields beta 2, which is the coefficient for SVI. That is, the expected change in log prostate-specific antigen for a 1-unit change in SVI is beta 2, holding all other covariates constant. Once we have estimated the parameters in our model, we may be interested in hypothesis testing. Beta sub j is the estimate of the partial slope of x sub j, or the effect of x sub j controlling for all other covariates in the model. We may be interested in testing the association between one covariate x sub j and the response y controlling for the other covariates. In that case, our null hypothesis is that the slope beta sub j is equal to 0 against the alternative hypothesis that the slope beta sub j does not equal 0. The test statistic is formed by dividing the estimated coefficient by its estimated standard error, which follows a t-distribution with n minus p plus 1 degrees of freedom. If the p-value is less than or equal to the predetermined type 1 error level alpha, we reject the null hypothesis. Otherwise, we fail to reject. We could also construct a confidence interval for our slope parameter estimate, which is preferred in some fields such as epidemiology and psychology. We can use the output from the summary function for hypothesis testing. Note the slope for log cancer volume is estimated to be 0.5612, and its standard error is estimated to be 0.1065. Dividing the estimate by its standard error yields this test statistic, which is 5.27. This statistic follows a t-distribution with n minus p plus 1 degrees of freedom, where n is the sample size and p plus 1 degrees of freedom are lost from estimating the p plus 1 parameters, the intercept, and the p slopes. In this case, n is equal to 67 and p is equal to 4, so the t-distribution has 67 minus 5, which equals 62 degrees of freedom. Because the p-value is less than the standard 0.05 level, we reject the null hypothesis and conclude that beta 1 is not equal to 0. However, the p-value for SVI is greater than the standard 0.05 level, so when testing the null hypothesis that the slope for SVI is equal to 0 against the alternative hypothesis that the slope for SVI is not equal to 0, we fail to reject the null hypothesis. Please keep in mind that failure to reject the null hypothesis indicates there is not a significant linear relationship between x sub j and y. That could mean that x sub j is not associated with y, or perhaps x sub j is associated with y, but the relationship is nonlinear. A partial F test is used to test whether a group of predictors is collectively associated with a continuous response. The null hypothesis is that all betas are equal to 0, and the alternative hypothesis is that at least one of the betas does not equal 0. This is the equation for calculating the test statistic for the F test. The full model includes the set of covariates of interest. The reduced model is the same as the full model, but with the covariates of interest removed from the model fit. The test statistic is based on the difference between the sum of squares due to the regression for the full model and reduced models, divided by the difference in those two models' degrees of freedom, and that resulting quantity is divided by the mean squared error for the full model. This test statistic follows an F distribution with the numerator degrees of freedom equal to the number of parameters being tested, and the denominator degrees of freedom equal to the number of degrees of freedom associated with error from the full model, which is n, the sample size, minus the quantity p plus 1, because there are p covariates in the full model plus 1 slope coefficient. As mentioned, Gleason grade is a multi-level factor, and therefore it is included in the model using dummy variables. As a reminder, because Gleason grade is either 6, 7, or greater than or equal to 8, R entered two dummy variables. Gleason 7 is 1 if Gleason grade is 7 and 0 otherwise. Gleason 8 is 1 if Gleason grade is 8 or higher and 0 otherwise. Gleason 7 equals 0 and Gleason 8 equals 0 represents a subject with Gleason grade of 6. That is why for a k-level multi-level factor, you only need k-1 dummy variables. For such a variable, rather than looking at the p-values which are compared to the referent group, in this case, the referent group is Gleason grade of 6, we usually perform a partial F test to test whether the group of predictors representing Gleason grade is collectively associated with a continuous response. That is, we want to test whether the set comprised of Gleason 7, Gleason 8 is associated with log prostate-specific antigen, controlling for log cancer volume and seminal vesicle invasion. The ANOVA function performs this test for us. In this case, the p-values indicate Gleason grade is not significantly associated with log prostate-specific antigen. The linear regression model includes 4 different assumptions, which can be remembered using the mnemonic line. This includes linearity. Because there are multiple predictors, component plus residual, also called partial residual plots, for each continuous predictor are examined. These are plots with a continuous predictor on the x-axis and the part of the fitted value that is from the particular x component on the y-axis. Independence, the error terms are independent of each other. Independence is assessed carefully by considering the study design. If subjects are recruited in clusters, for example, members of the same household, or if the subjects contributed multiple repeated measurements to the data set, the independence assumption is violated. Normality of errors. The error terms are normally distributed. And equal or constant variance. That is, the variability of the errors is the same for all values of x. This latter assumption is often called homoscedasticity. In other words, it assumes that the variance is the same for any level of x, or that the variance of y at each level of x is constant. These later two assumptions can be examined using the residuals. So residuals are simply the difference between the observed value of y and the fitted or predicted value of y. For checking linearity, the component plus residual plot can be constructed using the crplots function in the car-r package. The linear fit is included with a smooth curve from the loess overlaid. If the smooth loess curve does not lie approximately on top of the linear fit, linearity is not met for that continuous variable. If the linearity assumption is met, these two lines should be almost coincident. When using the plot function on the multivariable model, R provides a scatter plot of residuals versus fitted values, a normal quantile plot of residuals, and a plot of Cook's distance. The scatter plot of residuals versus fitted values can be used to assess equal variance, which should be indicated by observing a random scatter about the horizontal line at 0, such that there is equal spread up and down all along the plot. If you see a fan-shaped pattern in the residual versus fitted plot, that would indicate equal or constant variance assumption is violated. The normal quantile plot of the residuals is used to check whether the model meets the assumption that the errors are normally distributed. This is a plot of the observed residuals against the theoretical quantiles of the normal distribution. If the residuals are approximately normally distributed, the points on this plot should be a straight line. We should also check for outliers on the residual plot, as outliers may have undue influence on the fitted regression model. We should never just throw out data points because they are outliers. Only remove data if it is confirmed to be a mistake, for example, a data entry error. Plots of the square root of the standardized residuals versus the fitted values and Cook's distance can be used to identify outliers. We may also want to examine a plot of our observed outcome y plotted against the predicted outcome to see if the fitted linear model looks reasonable. When evaluating a predictor of primary interest, as mentioned, we can estimate the effect of one predictor while controlling for the effects of others. This is to control for confounding. Confounding is a distortion in the estimated measure of association that occurs when the primary predictor of interest, x sub 1, is associated with some other factors, say x sub 2 to x sub p, that are associated with the outcome. If we are interested in the effect of x sub 1 on y, and x sub 2 to x sub p are possible confounders, we can include x sub 2 to x sub p as predictors in our regression model. This results in an unbiased estimate of the true association between x sub 1 and y. As mentioned, one interest may be to use our multivariable model for prediction. Suppose we have a new subject, and for that subject we have measured all the covariates included in our multivariable model. We can predict this subject's response by plugging in their covariate values into the estimated equation. For example, if a new subject has log cancer volume of 1.35 with seminal vesicle invasion and a Gleason grade of 6, his predicted log prostate-specific antigen would be 2.62. The predict function takes a model object as a required argument and predicts the response. By default, predictions for the data are used to fit the model or output. If you specify a new data frame, the predictions will be output for those new observations. On the left-hand side, the figure displays the model predictions for the data used to fit the model. These data are typically called training data. On the right-hand side, the model predictions are for an independent data set not used to fit the model. Typically, these are called a test set. We will revisit using an independent test set and related approaches later in this module.